June 6, 1944, Omaha Beach. Cinematic depictions often highlight the brutal realities of combat, showcasing the harrowing moments when landing craft ramps lowered, unleashing waves of soldiers onto the exposed sands amidst a torrent of machine gun fire. However, what these dramatizations frequently omit is the agonizing prelude to battle, the prolonged period of waiting. Thousands of servicemen were confined within cramped steel vessels, circling offshore for seemingly endless hours. Many succumbed to debilitating seasickness, their stomachs churning as they observed the relentless march of time, acutely aware that German artillerymen were meticulously zeroing in on their predictable movements. This nightmarish scenario, fraught with peril, was never intended to unfold as it did. The only reason it did not culminate in an unmitigated catastrophe can be attributed to the ingenious and unwavering determination of a single boat builder from New Orleans, who had ingeniously resolved a formidable engineering challenge that the entire United States military had previously deemed insurmountable. Let us transport ourselves back to 1941. The American military establishment found itself confronted with a daunting logistical and mathematical conundrum. Their objective was to successfully disembark 150,000 troops onto hostile beaches, meticulously defended by what was arguably the most fortified coastline in recorded human history. The existing methods for amphibious landings were, to put it mildly, absolute fiascos. The British had endured this harsh lesson firsthand during the Gallipoli campaign in 1915, where troops attempting to row ashore in flimsy wooden boats were mercilessly cut down before their boots even touched the sand. By the advent of World War II, the majority of naval forces still adhered to a fundamentally similar approach. Colossal ships would anchor a considerable distance offshore, subsequently deploying smaller boats via davits. These ancillary vessels would then either be rowed or motored towards the beachhead. Soldiers were compelled to clamber precariously over the sides of these boats, plunging into chest-deep water while simultaneously burdened with 60-pound packs, a maneuver both perilous and exhausting. The inherent problems associated with these methods proliferated with alarming rapidity. Firstly, the unforgiving laws of physics presented a significant obstacle. A soldier attempting to navigate the gunwale of a boat while it was being violently buffeted by waves smashing against the shore faced, at best, a mere 40% probability of avoiding a debilitating ankle fracture. Secondly, the issue of exposure was critical. For approximately 30 seconds, each disembarking soldier became an utterly defenseless target, starkly silhouetted against the sky, a prime target for enemy fire. Thirdly, the efficiency, or rather the lack thereof, was deeply concerning. Unloading a single company, comprising approximately 120 men, could consume anywhere from 45 minutes to a staggering 2 hours, contingent upon the prevailing surf conditions. Fourthly, and perhaps most critically, these methods rendered it impossible to transport essential vehicles, jeeps, artillery pieces, and tanks, the very instruments of warfare that were indispensable for achieving victory in battle. These vital assets remained marooned on the larger ships, as there existed no viable mechanism to drive them off a boat into 3 feet of water. The British military had devised one particular solution: specialized landing ships equipped with bow doors. However, these were colossal vessels that necessitated beaching themselves directly onto the shore. Once grounded, they became immobile and highly vulnerable for extended periods, transforming into static, inviting targets for enemy bombardment. The Japanese had also experimented with their Daihatsu-class landing craft, yet even these designs still mandated that troops disembark by leaping over the sides. Essentially, every navy across the globe was grappling with the identical fundamental equation: How does one effectively transform a boat into a functional bridge between sea and land? Now, the narrative takes a fascinating turn. In September 1941, the United States Marine Corps issued a technical requirement that, to many, sounded like something plucked from the realm of science fiction. They sought a vessel capable of carrying 36 combat-loaded troops, hitting a beach at maximum velocity, disembarking those troops onto dry sand in less than 10 seconds, then reversing off the beach and returning for an additional load, all within a round-trip timeframe of under 15 minutes. The truly audacious stipulation was that this craft needed a draft sufficiently shallow to navigate coral reefs, yet simultaneously stable enough to endure arduous open ocean crossings. Oh, and one final, seemingly insurmountable demand: it needed to be economically viable enough to be manufactured by the thousands, and sufficiently straightforward in its operation that 19-year-old coxswains could pilot them competently under intense enemy fire. Every prominent shipyard in America, upon reviewing these exacting specifications, delivered a unanimous verdict: impossible. The very hull shapes required for shallow draft and inherent ocean stability were fundamentally contradictory. A bow ramp robust enough to support the dynamic weight of running troops would inevitably prove too heavy. Furthermore, the hydraulic systems, they argued, would inevitably fail in the corrosive saltwater environment. The litany of technical objections was so extensive that it filled multiple three-ring binders. Yet, amidst this chorus of skepticism, there was a singular individual operating out of Louisiana who persistently appeared at Navy procurement offices, clutching a rudimentary wooden model, and sporting an unwavering grin, adamantly asserting that he had already constructed the very contraption they deemed unattainable. They dismissed him as a madman. It turned out he was simply a visionary from New Orleans. Andrew Jackson Higgins embodied precisely the type of individual military bureaucrats typically disdained. He was self-taught, notoriously loudmouthed, possessed no properly fitting suit, and harbored the infuriating propensity to be undeniably correct when every credentialed expert with a college degree declared him wrong. Born in Nebraska in 1886, Higgins had dedicated 3 decades of his life to constructing shallow draft boats for a diverse clientele, including oil prospectors, trappers, and even rum runners navigating the intricate bayous of Louisiana. While meticulously trained Naval Academy graduates were preoccupied with designing sleek, formidable destroyers, Higgins was meticulously perfecting the art of floating a half-ton engine through 18 inches of swamp water without succumbing to the obstruction of a cypress knee. His company, Higgins Industries, remained entirely off the military's radar until 1938. For years, the Marine Corps had been rigorously testing various designs for landing craft, all of which had proven to be abject failures. They had witnessed these experimental boats grounding out 50 yards from shore, capsizing sideways in the surf, or having their propellers hopelessly entangled and damaged on treacherous sandbars. Then, a junior officer recalled a fleeting rumor about this eccentric Cajun, who crafted boats that could, as the local saying went, run on heavy dew. The Marines, primarily to fulfill a bureaucratic formality, dispatched observers to New Orleans. Higgins promptly loaded them into his latest swamp boat, christened the Eureka, and proceeded to demonstrate its capabilities by driving it at full throttle onto a mudflat, executing a swift, sports car-like turn, and then effortlessly motoring back into deeper water. The astonished observers immediately cabled Washington. "You need to see this immediately." What truly distinguished Higgins' design as revolutionary, and simultaneously provoked the ire of established shipbuilders, was his audacious rejection of conventional maritime wisdom. Standard naval architecture dictated that a boat's bow should be sharply pointed to efficiently cleave through water. Higgins, however, fashioned a bow reminiscent of a snow shovel, flat, broad, and angled distinctly upward. Traditional wisdom also mandated a deep keel for optimal stability. His boats, conversely, possessed virtually no keel whatsoever, merely a shallow, semi-tunnel protecting the propeller. The overall hull shape appeared, to the trained eye, fundamentally incorrect. It felt wrong to anyone steeped in conventional marine engineering principles. Yet, in the challenging environment of the Louisiana swamps, it functioned with an almost magical efficacy. The initial reaction from the military establishment was a potent mixture of contempt and suspicion. Engineers from the Bureau of Ships meticulously authored lengthy technical papers, painstakingly elucidating why the Eureka's design ostensibly violated fundamental hydrodynamic principles. They contended that the flat bow would generate excessive drag. They argued that the shallow draft would render it uncontrollable in strong currents, and that the protected propeller tunnel would inevitably lead to severe cavitation problems. Higgins, undeterred, extended an invitation for them to witness demonstrations in New Orleans. They politely declined, citing budgetary constraints. The unspoken translation was clear. "We are not squandering government funds on swamp boat nonsense when reputable shipyards are diligently developing proper landing craft." However, the Marines persisted in their advocacy, primarily because they were the ones who would ultimately bear the burden of storming beaches, and they possessed an intuitive understanding that eluded the desk-bound admirals. In April 1941, the Navy finally acquiesced to conducting competitive trials in Norfolk, Virginia. For prominent shipyards proudly presented their designs. 3 of these contenders hailed from well-established maritime companies boasting impeccable, gilt-edged reputations. Higgins, in stark contrast, arrived with 3 of his boats unceremoniously strapped to a barge. He brought no blueprints, only the tangible hardware itself. The official evaluation criteria encompass seaworthiness, speed, maneuverability, durability, and, crucially, the paramount ability to extract itself from a beach. The results of these trials were unequivocally one-sided. Higgins' boats achieved beaching speeds of 9 knots, rode smoothly onto the sand, backed off in under 30 seconds, and repeated this impressive feat repeatedly, 20 times without once fouling the propeller or incurring any damage to the hull. The competition fared dismally. One boat buried its bow so deeply that it refused to budge. Another's propeller was irrevocably shattered upon its very first grounding. The third managed to get on and off the beach once, only to immediately begin taking on water. By the second day of trials, Navy observers were discreetly revising procurement protocols. By the third day, Higgins had secured a lucrative contract for 1,500 boats, and remarkably, he still had not yet unveiled his truly audacious, crazy idea. The Eureka boat, while groundbreaking, had only solved half of the complex problem, successfully reaching the beach and then disengaging. However, troops were still compelled to clamber precariously over the sides, and, critically, there remained absolutely no practical method for driving a jeep directly out of the vessel. Higgins was acutely aware of this limitation. For 2 years, he had been meticulously sketching potential solutions in the margins of napkins, yet every design invariably encountered the same insurmountable obstacle, the immutable laws of physics. Incorporating a ramp at the bow necessitated hinges, and hinges, by their very nature, introduced a critical weak point precisely where the boat experienced the most intense flexing. The forces involved were utterly absurd. One had to envision a steel plate 4 feet wide and 8 feet long, simultaneously supporting 6 men, each weighing 250 pounds with full gear, while the boat pitched violently in 3-foot swells. This translated to an astonishing 1,500 pounds of dynamic force bouncing on a hinge every 2 seconds. Engineers calculated that such immense stress loads would inevitably cause any hinge mechanism to snap within a mere week of continuous saltwater operations. Then, in late 1941, a Marine Corps officer named Victor Krulak presented Higgins with a photograph that irrevocably altered his perspective and approach. Krulak had served as an observer in Shanghai in 1937, where he had witnessed the Japanese assault Chinese positions along the Yangtze River. The photograph depicted a Japanese Daihatsu landing craft featuring a ramp at its bow, not over the sides, a true ramp. Higgins reportedly scrutinized that image for perhaps 10 seconds, then allegedly uttered something unprintable about how the Japanese had grasped the fundamental concept correctly, but had faltered in its execution, primarily because their ramp still necessitated troops wading through ankle-deep water. It was at this pivotal juncture that Higgins' extensive experience with swamp boats shifted into overdrive. The Japanese design incorporated a ramp that simply angled downwards into the water. While perfectly adequate for calm rivers, this approach proved utterly useless in volatile surge zones, where every incoming wave dramatically altered the water's depth by several feet. Higgins astutely realized that the ramp could not merely drop. It had to execute a dual motion, dropping and simultaneously extending the hull forward, thereby creating an unbroken bridge from the boat's deck directly onto the dry beach. The underlying geometry sounds deceptively simple until one embarks upon the actual construction. The ramp itself needed to maintain the identical angle as the bow, which in its design was a precise 45 degrees. When raised, it seamlessly integrated to become the bow itself, functioning as a watertight continuation of the hull. When lowered, it had to lock into a perfectly flat and stable position, sufficiently robust to allow a 5,000-pound Jeep to drive across it at speed without exhibiting more than half an inch of flex. The challenge of bridging a gap exceeding half an inch was met with Higgins' remarkably robust engineering. His approach embodied sheer mechanical resilience, featuring a system of 2 powerful hydraulic cylinders that exerted force against steel cables. This primary mechanism was prudently augmented by manual chains, serving as a critical failsafe should the hydraulic system encounter any operational difficulties. The ramp itself was constructed from formidable quarter-inch steel plate, further fortified by I-beams meticulously welded to its underside. While inherently heavy, this substantial mass proved advantageous. Upon impacting the sandy terrain, its sheer momentum and considerable weight ensured it remained firmly anchored. The pivotal connections were far from fragile articulation points. Instead, they comprised colossal pin assemblies, each measuring 4 inches in diameter, a scale typically associated with the construction of formidable drawbridges. While acknowledging the inherent possibility of their failure, their design guaranteed sufficient operational longevity to fulfill their crucial mission. Furthermore, Higgins ingeniously conceived the entire apparatus to allow a crew to swiftly replace a damaged hinge in a mere 20 minutes, utilizing only basic tools like a sledgehammer and a cheater bar. By May 1942, the inaugural prototype was complete. Higgins himself designated his creation the LCP, an acronym for Landing Craft, Vehicle, Personnel. However, the armed forces quickly adopted the moniker Higgins Boat, a designation Andrew Higgins personally disliked, preferring that recognition be bestowed upon his dedicated team of engineers. The Marine Corps transported this innovative vessel to Solomon's Island, Maryland, for rigorous evaluation. The assessment team proceeded to load the craft with an entire platoon of soldiers augmented by a jeep, an unprecedented feat for any landing craft globally at that juncture. They then navigated towards a designated beach, meticulously observing the unfolding sequence. The ramp swiftly descended, allowing the jeep to disembark in a mere 4 seconds, followed by the troops in an additional 6 seconds. The ramp then retracted, and the vessel reversed into deeper waters. The entire cycle, from initial grounding to complete withdrawal, consumed a remarkable 13 seconds. The commanding officer overseeing the trial promptly relayed his findings to Washington, declaring, "Specifications met. Recommend immediate mass production." Within a mere 3 weeks, Higgins secured a monumental contract for 10,000 units. Despite this urgent procurement, the Pentagon harbored lingering doubts about the design's potential efficacy in actual combat scenarios, yet their strategic desperation compelled them to take this calculated risk. Years following the cessation of hostilities, Dwight D. Eisenhower articulated a sentiment so profound it warrants permanent inscription, perhaps even in marble. "Andrew Higgins is the man who won the war for us. If Higgins had not designed and built those landing crafts, we never could have landed over an open beach. The whole strategy of the war would have been different." Such a declaration, emanating from a 5-star general who orchestrated the most extensive amphibious invasion ever recorded in human history, transcends mere exaggeration. It stands as an unequivocal admission of the pivotal role played by Higgins' innovation in shaping the conflict's outcome. Nevertheless, a deeper examination of the empirical data reveals a reality that somehow surpasses the most extraordinary legends. The pivotal date was August 7, 1942, at Guadalcanal, marking the initial significant trial of the Higgins boat amidst the crucible of combat. The 1st Marine Division faced the formidable task of disembarking 11,000 troops onto shores staunchly defended by 2,800 entrenched Japanese soldiers, who had benefited from months of meticulous preparation. Conventional pre-war military doctrine had projected that such an extensive operation, involving the deployment of all personnel and their requisite equipment, would necessitate an arduous 14 to 18 hours. Yet, the actual chronology of events was astonishing. A mere 4 hours and 17 minutes elapsed from the moment the first landing craft touched the sand until the final rifle company had established its defensive positions. Marine logistics officers, witnessing this incredible efficiency, initially suspected their stopwatches were malfunctioning. They radioed the offshore transports with incredulity. "Confirmed troop counts. This can't be right." The transports, in turn, verified the accuracy of the figures. Every man was accounted for, alongside an additional 73 vehicles, which, according to established tactical doctrine, were not supposed to be landed on the opening day of the assault. The underlying mechanical genius that facilitated this unprecedented speed was truly remarkable. A solitary Higgins boat possessed the capability to complete the entire beach-to-transport circuit, encompassing grounding, methodical unloading, swift reversal, motoring back to the transport, and efficient reloading, within a timeframe of 11 to 15 minutes, contingent upon the distance involved. This extraordinary efficiency stands in stark contrast to the performance of British landing craft deployed 3 weeks later at Dieppe, which required an average of 32 minutes per operational cycle and, critically, often proved incapable of extracting themselves, resulting in scores of soldiers becoming stranded as the tide receded. At Guadalcanal, the initial assault wave comprised 87 Higgins boats. A straightforward calculation illuminates their impact. 87 boats executing 4 trips per hour collectively delivered 348 boatloads every 60 minutes. Given that each vessel could transport 36 men, or 1 vehicle complete with its crew, this arithmetic translates to an astonishing rate of over 12,000 personnel equivalent movements per hour. Evidently, The limiting factor was not the boats themselves, but rather the speed at which they could be loaded from the transport ships. The harrowing events of Tarawa in November 1943 presented the ultimate crucible for the 3-minute operational claim, unfolding under truly nightmarish circumstances. The Navy's hydrographic charts proved catastrophically inaccurate. The tide was a critical 18 inches lower than forecasted, and an unforgiving coral reef stretched an imposing 500 yards from the shoreline. Larger landing ships found themselves hopelessly grounded, rendered immobile. Yet, the Higgins boats, with their remarkably shallow draft of only 3 feet, glided effortlessly over the treacherous reef as if it were non-existent. Wave after relentless wave, every 3 to 4 minutes, another boat reached Red Beach. The Japanese defenders had meticulously pre-sighted their machine guns and mortars on the waterline, anticipating leisurely moving targets. Instead, they were confronted with a relentless, human conveyor belt. The Marines endured horrific casualties, suffering over 1,000 fatalities within 76 hours. Nevertheless, their advance persisted, fundamentally because the landing craft maintained their unceasing operation. Japanese commander Keiji Shibasaki had famously asserted that it would require 1,000,000 men and a century to conquer Tarawa. The Marines achieved victory in a mere 3 days, a triumph largely attributable to the Higgins boats' ability to deliver reinforcements with a speed that outpaced the defenders' capacity to inflict casualties. In July 1943, Operation Husky, the monumental invasion of Sicily, saw a staggering armada of 2,590 landing craft of various designs simultaneously assault 26 distinct beaches. Higgins boats constituted approximately 1,400 of this colossal fleet. The operational tempo achieved was nothing short of surgical in its precision and relentless efficiency. Vessels grounded, discharged their cargo, withdrew, and promptly returned with such an unwavering rhythm that beach masters found themselves orchestrating arrivals with the meticulous coordination of air traffic controllers. Some individual boats managed to complete an astounding 14 round trips within the initial 12 hours. Crews, pushing past the brink of physical exhaustion, navigated by sheer instinct and executed loading procedures through ingrained muscle memory. Subsequent to the operation, when Navy analysts meticulously compiled after-action reports, they discovered that the average Higgins boat deployed at Sicily had successfully delivered 468 troops or 23 vehicles over 3 continuous days of unrelenting operation. Multiplying this impressive figure across the 1,400 Higgins boats involved provides a clear understanding of why German forces proved utterly incapable of reinforcing their positions rapidly enough to mount an effective counterattack. The climactic moment arrived on June 6, 1944, with the D-Day landings in Normandy. More than 1,500 Higgins boats formed the spearhead of the initial assault waves across 5 designated beaches. At Utah Beach, records indicated an astonishing frequency, with landing craft arriving every 3.2 minutes during the most intense periods. Omaha Beach, however, descended into unmitigated chaos. German defenses proved far more formidable and resilient than intelligence assessments had anticipated. Yet, even amidst this brutal maelstrom, the Higgins boats maintained their relentless advance, never ceasing their deliveries. It was this sheer, unwavering volume, rather than heroism in isolation, that ultimately shattered the German defensive lines. While an enemy might effectively repel the initial wave, or even the second, the sustained onslaught of the 8th, the 15th wave, this relentless persistence, was made possible, indeed guaranteed, by the continuous operation of these indispensable landing craft. Intriguingly, the Japanese military possessed visual evidence. They had observed and indeed developed their own Daihatsu landing craft, a vessel that, remarkably, had pioneered the innovative bow ramp concept as early as the 1930s. This raised a perplexing question. Why then did they not construct a craft as demonstrably effective as the Higgins boat? This enigma persistently troubled Allied intelligence officers throughout the protracted Pacific campaign, primarily because with each Japanese-held island captured by U.S. forces, they consistently discovered landing craft that appeared functionally similar but ultimately proved deficient in several critical aspects. The resolution to this puzzling disparity illuminates a profound insight into how divergent engineering philosophies can profoundly influence the very conduct and outcomes of warfare. The Daihatsu-class landing craft, initially deployed in 1937 during the tumultuous Second Sino-Japanese War, bore a superficial resemblance to Higgins' innovative design. It featured a bow ramp, a relatively shallow draft, and the purported capability to beach and retract. However, the Japanese engineers had meticulously optimized their vessel for an entirely distinct set of operational environments. Their principal missions were conducted along inland rivers and within the placid coastal waters of China and Southeast Asia, regions characterized by predictable tides, opportunities for advanced beach surveys, and generally protected aquatic conditions. Consequently, the Daihatsu incorporated a deeper V-hull, which conferred superior efficiency and greater speed in tranquil waters under ideal circumstances. This very design choice, however, rendered it catastrophically inadequate in surf conditions. When ocean waves impacted the V-hull at an oblique angle, the craft would uncontrollably skew sideways, occasionally even capsizing entirely. The ramp mechanism itself served as a telling exposition of these fundamental design divergences. Japanese engineers opted for a lightweight ramp that descended into the water at a markedly steep angle. While this configuration proved perfectly serviceable for disembarking onto a riverbank with a mere 6 inches of water, its utility dramatically vanished when encountering a beach assailed by 2-foot surf. In such conditions, troops were compelled to wade through knee-deep water, thereby sacrificing precious speed, relinquishing the element of surprise, and becoming exposed targets for enemy fire. Following their capture of Daihatsu craft at Guadalcanal, the Marines subjected these vessels to thorough testing. Their subsequent assessment was unequivocally brutal. Ramp does not extend hull line. Vehicle operation impossible in surf conditions. Extraction from beach inconsistent due to underpowered engines and hull design. This, however, represented an even more profound miscalculation. The Japanese engineers fundamentally failed to grasp that Higgins' seemingly unrefined, blunt bow was not a design concession. It was, in fact, the very essence of its revolutionary effectiveness. This distinctive, snow shovel, configuration enabled the boat to surge onto the beach at considerable speed, leveraging its momentum to ascend the sandy incline until the ramp could be deployed directly onto dry ground. In stark contrast, the Daihatsu's sharper bow would invariably dig into the sand, causing the vessel to become firmly mired. Japanese crews attempted to compensate for this inherent flaw by adopting a slower approach to the beach, inadvertently granting defenders additional time to accurately target them. At Tarawa, U.S. forces encountered numerous abandoned Daihatsu craft that had initially beached successfully but subsequently proved incapable of reversing off. Their propellers had either struck submerged coral formations, or their hulls had settled too deeply into the soft sand. These vessels, once intended for transportation, had effectively been transformed into static, vulnerable bunkers. Ultimately, the Imperial Japanese Navy did endeavor to directly emulate the highly successful Higgins boat design. By 1944, Japanese engineers meticulously scrutinized captured LCDPs from the Philippines, subsequently developing comprehensive specifications for a domestic variant. However, by this advanced stage of the conflict, Japan's industrial capacity was in a precipitous state of decline. While they possessed the detailed blueprints, they critically lacked the requisite manufacturing infrastructure to produce sophisticated hydraulic systems in the vast quantities demanded by wartime exigencies. Even more significantly, they were severely deficient in the necessary shipyard workforce. Higgins Industries, by contrast, had effectively utilized semi-skilled laborers, who could be trained to weld hull sections in a matter of weeks, not years. Japan's deeply ingrained traditional shipbuilding culture, however, placed its reliance on highly specialized master craftsmen, a model utterly incapable of scaling to meet the immediate, urgent demand for thousands of landing craft. A staggering number of boats were needed instantly. A poignant Japanese naval assessment from late 1944 reveals a stark contrast in design philosophies. The author, an engineering officer, observed that American landing craft exhibited crude but effective design principles that sacrificed elegance for mass production and rough water performance. He further noted that these American vessels could be manned by inexperienced personnel due to their simplified controls and a hull design that was remarkably forgiving of operator errors. In stark opposition, Japanese landing craft demanded highly skilled coxswains for proper handling. The officer's concluding remarks highlighted a fundamental philosophical divergence. Japan had prioritized quality, while the Americans had grasped that the war's ultimate victory would hinge on sheer quantity. This profound difference, he lamented, could not be remedied simply by replicating a hull shape. By 1945, while Japanese forces in the Pacific still relied on Daihatsu craft that necessitated troops leaping into the water, every American amphibious assault had evolved into a textbook demonstration of mechanized efficiency. The Japanese had indeed pioneered the bow ramp concept, but had never fully realized its immense potential. Higgins, however, seized upon their initial idea, comprehended its true purpose, and meticulously re-engineered it from fundamental principles. This was not mere imitation. It was a profound evolutionary leap. August 7, 1942. Guadalcanal. Theoretical assumptions were about to collide violently with the harsh realities of coral reefs, Japanese machine gun fire, and an overwhelming pandemonium that rendered engineering textbooks seem utterly quaint. The Higgins boat had previously performed flawlessly in controlled water tests conducted at Norfolk and Solomon's Island. However, these were sterile environments with meticulously surveyed beaches and, crucially, no enemy combatants returning fire. Now, 87 of these vessels were surging towards Lunga Point, transporting the 1st Marine Division, and absolutely no one possessed certainty regarding the design's resilience under the crucible of actual combat stress. The initial formidable challenge was the reef itself. Pre-invasion reconnaissance had indeed detected its presence, but intelligence had severely underestimated both its extensive reach and the alarming shallowness of the water above it. Larger landing ships, specifically LSTs, which were engineered to transport tanks, became firmly grounded 400 yards from the shoreline, immovably stuck. Their ramps descended into a prohibitive 4 feet of water, rendering the disembarkation of tanks impossible without the catastrophic drowning of their engines. The Higgins boats, however, with their shallow draft of merely 3 feet when fully loaded, skillfully skimmed over the treacherous reef with mere inches to spare. Coxswains reported the unsettling sensation of the hull scraping against coral, accompanied by a sickening grinding sound, yet the boats steadfastly maintained their forward momentum. Higgins had deliberately over-engineered the hull bottom, incorporating double-riveted seams and reinforced keel guards, specifically anticipating that these vessels would inevitably collide with submerged obstacles. This meticulously paranoid design philosophy proved instrumental in salvaging the landing within the critical first 30 minutes. The second formidable challenge encountered was the precise composition of the beach. The sand at Lunga Point was fundamentally different from the firm, compacted type found on test ranges. It consisted of loose, volcanic material that readily shifted under any significant weight. Consequently, when the initial wave of boats made contact at full speed, their bows burrowed deeper than anticipated. Some vessels became embedded as much as 18 inches before their forward momentum was completely arrested. Crews, understandably, experienced moments of panic, believing their craft were hopelessly stuck. Then, the ramp hydraulics engaged. The substantial weight of the descending ramp actually contributed to leveling the boat, effectively redistributing its mass. Troops swiftly disembarked. The vessel lightened considerably, and coxswains vigorously engaged the engines in reverse. The vast majority of boats successfully extracted themselves in under 40 seconds. A few required second attempts, maneuvering off at an angle to break the powerful suction. One boat commander later recounted that he had reversed, repositioned, and grounded his vessel 3 additional times to unload subsequent waves of troops. Remarkably, the hull absorbed this relentless abuse without exhibiting any signs of cracking. The third critical issue was the relentless enemy fire. It was in this harrowing context that the mechanical simplicity of the Higgins boat paid unforeseen dividends. Japanese defenders meticulously targeted the incoming vessels with a barrage of mortars and machine guns. Bullets relentlessly perforated the plywood gunnels. Higgins had judiciously employed plywood for the boat's sides to conserve weight, reserving steel exclusively for the ramp and the hull bottom. Troops instinctively crouched behind the ramp for vital protection, a strategy that proved effective because that quarter-inch thick steel was robust enough to withstand rifle rounds. However, the truly pivotal aspect emerged when hydraulic lines were severed by shrapnel, an unfortunate occurrence for 11 boats in the initial wave. In these instances, crews swiftly switched to manual chains, with 2 men strenuously cranking handles. While the ramp descended in 18 seconds instead of the customary 6, it still descended. This inherent redundancy, a primary hydraulic system complemented by a manual backup, ensured that even damaged boats remained fully operational. The fourth significant challenge revolved around sustainment. Over the ensuing 3 days, those 87 boats operated without cessation. There were no dedicated maintenance facilities, no readily available replacement parts, only tireless crews executing field repairs between their runs. They resorted to using seawater as a coolant when their freshwater supplies were depleted. Bullet holes were expediently patched with tar and canvas. One particular boat suffered the complete loss of its hydraulic system when a mortar fragment utterly destroyed the pump, yet its resilient crew manually operated it for 2 full days, completing 23 trips, until a proper repair ship finally arrived. Higgins had ingeniously designed every major component to be replaceable using only hand tools and brute force. If a propeller sustained damage, crews carried a spare and could swap it out in a mere 20 minutes. Should a ramp hinge crack, they simply bolted on a backup plate and continued their vital operations. The comprehensive after-action reports from Guadalcanal ultimately filled 3 substantial binders. Navy maintenance teams meticulously inspected every boat after the initial week of intense combat. They discovered a range of issues, including stress fractures, worn bearings, and corroded fittings, but notably, there were no catastrophic structural failures. The average boat had been grounded an astonishing 31 times, endured multiple direct hits, operated continuously in saltwater without proper maintenance, and yet remained an impressive 87% mission capable. Engineers had initially projected a 40% failure rate within the first 48 hours of combat operations. The actual observed failure rate was a remarkably low 9%, and the majority of these failures were attributed to boats that sustained direct hits from artillery. Guadalcanal did not merely validate the efficacy of the Higgins boat. It unequivocally demonstrated that an unglamorous, robustly overbuilt, and inherently idiot-proof design profoundly surpasses elegant engineering when human lives are actively at stake. Here is where the narrative takes a truly extraordinary turn. In December 1941, Higgins Industries was a relatively modest regional boat shop, employing a mere 75 individuals and constructing perhaps a dozen craft each month. By December 1944, it had undergone an astonishing metamorphosis, emerging as the largest private employer in Louisiana, boasting over 20,000 workers, operating 7 expansive plants spanning 30 city blocks, and delivering an incredible 700 boats every single month. This was not merely scaling production. It was an act of industrial sorcery. Andrew Higgins accomplished this remarkable feat by systematically flouting every manufacturing rule that the government had vehemently insisted was sacrosanct. The military's procurement office held very rigid preconceptions regarding the proper functioning of shipbuilding. Their established protocol dictated hiring highly trained shipwrights, who had dedicated years to mastering their craft. Boats were to be constructed individually, from inception to completion, with the same dedicated crew overseeing each vessel through its entire build process. Furthermore, strict quality control was to be meticulously maintained, with inspectors providing sign-offs at every discrete stage. Higgins, however, observed this traditional model and essentially retorted, "That's charming, but we require 20,000 boats within 3 years. So observe this." He boldly adopted a manufacturing innovation from Henry Ford that the entrenched maritime industry considered outright heresy: the assembly line production method. "Boats do not traverse factories," shipbuilders adamantly insisted. Higgins, undeterred, ensured that they did move anyway. He ingeniously segmented the LCVP construction into 14 major sub-assemblies. Station 1 was dedicated to the fabrication of the bow ramp and its intricate hydraulic systems. Station 2 meticulously constructed the various hull sections. Station 3 expertly handled the engines and drive systems. Workers became highly specialized in a single, repetitive task: welding a particular seam, riveting a specific joint, or wiring one electrical system. A young individual from rural Louisiana, who had never even glimpsed the ocean, could master the skill of welding a perfect hull seam in a mere 2 weeks. The traditionalists vociferously protested, asserting that this approach would inevitably yield inferior boats. Higgins's decisive response was to extend an invitation to Navy inspectors to rigorously test randomly selected boats directly from the assembly line. The resulting failure rate was an astonishingly low 2.1%, a performance superior to that of traditional shipyards producing unique, one-off vessels with highly esteemed master craftsmen. The workforce itself became a revolutionary force. Higgins hired anyone capable of wielding tools: women, black workers, elderly men well past draft age, and even teenagers on summer break. In 1940s New Orleans, this was an utterly radical approach. The company integrated its factories years before the military itself integrated its units. Black and white workers shared the same assembly lines, ate in the same cafeterias, and utilized the same bathroom facilities. Higgins's rationale was rooted in pure pragmatism. I don't care if they're purple with pink polka dots. Can they weld? Yet, the societal impact of this policy was profound. By 1943, an impressive 18% of his workforce was black, and 40% were women. Rosie the Riveter was not merely an iconic poster in New Orleans. She was actively constructing the very boats that would ultimately secure victory in the war. The production tempo was utterly relentless. In June 1944, the pivotal month of D-Day, Higgins Industries delivered an astonishing 737 landing craft. This translates to an average of 24 boats per day, or one boat every 60 minutes, achieved through continuous three-shift operations around the clock. The plants never ceased their activity. Welding arcs brilliantly illuminated the night sky, resembling a continuous, mesmerizing lightning storm. Workers routinely clocked 60-hour weeks as standard, with 80-hour weeks becoming commonplace prior to major invasions. The company paid premium wages, an impressive $1.20 per hour when the national average hovered around 65 cents, because Higgins profoundly understood that exhausted, financially struggling workers construct inferior boats. Conversely, well-paid, highly motivated workers could consistently maintain exceptional quality while simultaneously meeting incredibly demanding quotas. Raw materials, rather than labor, eventually emerged as the primary bottleneck. A single LCVP demanded 1.2 tons of steel plate, 80 feet of hydraulic line, 340 rivets, 15 gallons of marine paint, and one powerful 225 horsepower gray marine diesel engine. Multiplying these requirements by 700 boats monthly necessitated a staggering 840 tons of steel, 56,000 feet of hydraulics, and 238,000 rivets every single month, all delivered precisely on time, without any exceptions. Higgins proactively established direct relationships with prominent steel mills in Pittsburgh, crucial rubber plants in Akron, and essential engine manufacturers in Detroit. He completely circumvented military logistics channels when procurement officers demonstrated excessive sluggishness, sometimes even acquiring materials on the private market at a higher cost simply to adhere to his stringent delivery schedules. The Pentagon initially disdained this unconventional, cowboy approach until they gradually recognized that the boats consistently materialized exactly when they were promised. Up exactly when promised. By the cessation of hostilities, Higgins Industries had achieved an astonishing manufacturing output, fabricating a grand total of 20,094 vessels. This impressive fleet encompassed not only the ubiquitous LCVPs, but also larger landing craft mechanized, LCMs, swift PT boats, and various other specialized naval craft. Remarkably, this production volume surpassed the combined efforts of all other American boat manufacturers, underscoring the company's unparalleled contribution. Indeed, Higgins's enterprise was responsible for an astounding 92% of the Navy's entire landing craft armada. When the Japanese Empire formally capitulated in August 1945, Higgins found itself holding orders for an additional 12,000 boats, which were, of course, instantly rescinded. Consequently, within a mere 6 months, the company's formidable workforce dramatically contracted from 20,000 employees to a mere 800. The industrial behemoth, which had ascended with such incredible speed, experienced an equally precipitous decline. Nevertheless, those 20,000 vessels had already fundamentally reshaped the trajectory of military history. At precisely 6:30 hours on June 6, 1944, the pivotal assault on Omaha Beach commenced, marking what would become the most renowned 6-hour period in the annals of amphibious warfare. Throughout this monumental undertaking, Higgins' boats, served as the indispensable connective tissue, seamlessly integrating the myriad components of the entire invasion. When one views those iconic, often grainy historical films or the meticulously crafted Hollywood cinematic depictions, one witnesses the grand culmination of a multifaceted endeavor, the iterative evolution of design, the miraculous feats of wartime manufacturing, and the rigorous crucible of combat testing. Crucially, however, these scenes also reveal the foundational blueprint that would inform and guide virtually every amphibious assault for the subsequent 8 decades, extending its influence right up to the present day. The statistical data emerging from the Normandy campaign is truly staggering, possessing a magnitude that often fails to fully register until one deliberately pauses to contemplate the intricate logistical demands. The initial waves of the assault alone deployed 1,089 Higgins boats across the 5 designated landing sectors. At Omaha Beach in particular, a remarkable 293 LCVPs executed the perilous journey from the transport ships to the embattled shore. Each of these versatile boats completed an average of 4.7 cycles, grounding, unloading, and extracting, within the critical first 12 hours. This translates to an astonishing 1,377 individual beach landings at a single location in just half a day. To fully grasp the intensity, one must envision a boat making landfall, discharging its cargo, and then disengaging approximately every 31 seconds during the peak periods of the operation. The German defenders were not merely contending with waves of Allied soldiers. They were confronting a sophisticated mechanical system specifically engineered to overwhelm them through sheer, relentless repetition. Even in instances where boats sustained direct hits, a total of 34 were tragically destroyed at Omaha by formidable obstacles, submerged mines, and devastating artillery barrages. The continuous flow of reinforcements ensured that the momentum of the assault scarcely faltered. The strategic doctrine that solidified in the aftermath of Normandy swiftly attained the status of military scripture. Contemporary amphibious operations, even those employing cutting-edge technology, continue to adhere to the fundamental Higgins template: successive waves of landing craft, precisely timed intervals between assaults, a continuous and robust resupply chain, and the direct deployment of vehicles onto the designated beaches. The United States Marine Corps' current landing craft air cushion, LCC, those futuristic-looking hovercraft that often appear to be plucked from the pages of science fiction, functionally operates on the identical principle as an LCP. While undeniably faster and more technologically advanced, their core mission remains unchanged: to transport troops and essential vehicles from ship to shore, and then to promptly disengage and repeat the critical task. Even the Chinese People's Liberation Army Navy meticulously scrutinized Normandy footage as they conceptualized and designed their indigenous Type 726 landing craft, with a keen eye towards potential operations involving Taiwan. The underlying geometric principles, it seems, have remained immutable: a protected approach, a deployable bow ramp, and the capacity for rapid egress. Yet, a crucial aspect often tends to be overshadowed in the fervent commemoration of D-Day. The profound and far-reaching impact of the Higgins boat extended well beyond the European theater of operations. Across the vast expanse of the Pacific, the arduous island-hopping campaign was, in essence, an immense Higgins boat conveyor belt, stretching an incredible 5,000 miles. Pivotal engagements at Guadalcanal, Saipan, Peleliu, Iwo Jima, and Okinawa, among countless others, were utterly dependent on these shallow draft workhorses. Their unique design allowed them to navigate treacherous coral reefs that would have rendered conventional, deeper draft landing ships utterly immobile. During the brutal Battle of Iwo Jima in February 1945, Marines successfully landed an astounding 30,000 troops within the initial 48 hours, utilizing 482 Higgins boats. These operations were conducted on beaches composed of such loose volcanic ash that many vehicles immediately sank to their axles upon disembarking. The boats, however, adapted with remarkable ingenuity. Their skilled coxswains quickly learned to approach the beaches at increased speeds, leveraging momentum to propel the craft over the most challenging, softest sections of sand. This exceptional operational flexibility, the inherent capacity to modify and refine techniques based on prevailing environmental conditions, was a direct outgrowth of the design's fundamental simplicity and robust engineering. Andrew Higgins, the visionary behind these transformative vessels, passed away in 1952, a mere 7 years after the global conflict concluded. He died largely unremembered by the broader public and teetering on the brink of financial ruin. His company proved unable to successfully pivot to peacetime production, a common fate for many wartime industrial giants. Military contracts, which had fueled his empire, abruptly evaporated, and he had, by necessity, leveraged every conceivable asset to meet the overwhelming wartime quotas, leaving no financial safety net whatsoever. The very man whom General Dwight D. Eisenhower famously credited with having won the war spent his final years embroiled in legal battles with creditors. There is no Grand Higgins memorial gracing the National Mall, nor has an aircraft carrier been christened in his honor. Most Americans, regrettably, have never even encountered his name. Nevertheless, if one has ever witnessed any cinematic or documentary footage depicting beach landings, whether from World War II, the Korean War, the Vietnam War, the Gulf War, or the Iraq War, one has undeniably witnessed his enduring legacy. Every single ramp that descends onto a sandy shore traces its conceptual lineage directly back to that ingenious swamp boat builder who so convincingly demonstrated to the Pentagon that a design, both ruggedly practical and, perhaps, aesthetically unrefined, profoundly outclasses one that is merely elegant but ultimately ineffectual. The contemporary United States military continues to operate landing craft that are direct descendants of Higgins's pioneering design. The modern landing craft utility, LCU, for instance, can meticulously trace its genealogical lineage through 7 distinct evolutionary stages, all leading back to the original LCDP. When Marines conduct their rigorous training exercises on the beaches of Camp Pendleton or Quantico, they are, in essence, executing operational procedures that were initially codified in 1943, procedures fundamentally predicated upon the unique capabilities of the Higgins boat. The prevailing military doctrine assumes the inherent ability to deliver troops and essential vehicles directly onto contested beaches at precisely measured intervals, a critical assumption that only became a practical reality because one determined engineer in New Orleans steadfastly refused to accept the notion that such a feat was impossible. Wars are undeniably won by formidable tanks, advanced aircraft, and the unparalleled bravery of individual soldiers, but sometimes, just sometimes, they are decisively swayed by what amounts to a glorified swamp boat equipped with a ramp on its front. General Eisenhower, a man of immense practical wisdom, understood this profound truth. The rest of us, it is argued, should endeavor to understand it too.